I mentioned HIV/AIDS and how the concern was in the 80s and early 90s that a third of the U.S. would be infected and possibly dying by the disease. And one thing to notice here, the red is 15 to 34%, and so there are parts of the world where that actually has happened. And when you look at the international number of cases, it's growing steadily and then it's topped off. Okay? Now, when we first started looking at HIV/AIDS, we had no idea when it would flatten out or how fast it would grow. All we could do is count AIDS cases, okay? And when we looked at AIDS cases, something unusual happened. In every model I've shown you up to this point, when you look at the number of cases as it grows as a function of time, it grows exponentially. Remember I mentioned, imagine R naught being 2. It goes 1, 2, 4, 8, 16. That's exponential growth. That's what we expect. That's what we're trained as epidemiologists to think one person infects 2 people, there are 1.5 people on average, and it grows exponentially. But when we look at the early AIDS epidemics, well, here's an example. So it grows exponentially. When it loses the exponential growth, that means it's topping off. The epidemic is reaching its peak, and then we expect it to go down, okay? And it was 1988 or 89, I was at the International HIV Conference, I was in Canada that year. And the Prime Minister of Canada came up and says, we've been looking at the AIDS data, it's not growing exponentially, we're at this part of the curve. In fact, he showed this curve. So 1989, the epidemic is almost over. And he was booed off the stage because it was clear something, you know, he was using elementary knowledge of epidemiology to a problem that was far more complex than that. In fact, when you look at the growth of the number of AIDS cases, no, it wasn't growing exponentially. In fact, if you look at the cumulative number of cases, the total number of people that have come down with AIDS as a function of time, 1982 to 1988, and you take the 1/3 power of that, it was a straight line. It wasn't growing exponentially, it was growing, so every 1/3 power means it's growing like a cubic polynomial. Number of cases is growing like t cubed. Exponential means it's growing like 10 to the t. So it wasn't growing like a normal epidemic. But on the other hand, when you look at it like this, it's kind of crazy to think that now this line's going to magically go down. You know, it's still growing. And so the first question is why is it growing this way? And so what you can do is you can cut the population and say, well, maybe it's a certain segment of the population. So we took the data, we looked at men having sex with men, it was a straight line. IV drug users, straight line. Heterosexuals, straight line. Northeast, straight. Central, southeast, black, white, Chicano, no matter how we cut the data, the number of cases was growing like a cubic polynomial. And it was so accurate. I mean, if I was running a class and asked someone to get real data and bring it in, and they showed me this data, I'd say, okay, that's a really nice plot. Why don't you go back and do the experiment now? I mean, this is real data. This is not fake lines. This is data off the CDC website. So the question is, why was HIV/AIDS growing so differently than all the other epidemics like gonorrhea and syphilis and influenza and historical epidemics like smallpox? What was different about HIV/AIDS? And the first thought was, maybe it's because it takes so long before someone gets AIDS and they're not equally infectious every year. So what happens when you're infected with HIV/AIDS, so this is time since infection, weeks, 6 years, 8 years. So first you get, and this is how infectious you are. You first get infected with the HIV virus, your immune system has never seen this guy before. And so it starts replicating like crazy inside you. You shed the virus just like in the flu, you're very infectious, but then your immune system works, it works really well. It drives that virus down to undetectable levels. It knows what to do with viruses. But what's different about HIV and say the flu virus is the HIV, during this time when it's reproducing, it hides inside your cells. It gets inside your blood cells, your macrophages, your T cells, your B cells, your blood cells, your stem cells. It gets inside your stem cells, inside your bone marrow, and where the immune system can't see it. And it kind of sits inside these macrophages, kind of happy as a clam. But then slowly it takes over the mechanism inside, the nucleus inside the macrophage to make copies of itself until it gets so fills the cell with copies of itself that the cell explodes, and then your immune system says, I've seen this guy, I know how to knock him down. It knocks him back down again. But enough of those get infect another macrophage, and it just keeps going on. So it's all, and it hides inside. I like to use the expression happy as a clam, and because I started thinking about this is how a starfish eats a clam. Think about a starfish, gloms onto the clam sitting there, just having a nice day. The starfish gloms onto him, and the clam closes shut and feels, the starfish has got no strength at all. I'm perfectly safe from the starfish. But the starfish just keeps very slowly, and the clamps. When's he going to go away? And after not too many minutes, 10, 20 minutes, the muscles in the clam cramp, opens up, the starfish has his dinner, goes off, finds another clam. That's what these HIV viruses are doing. They're inside your macrophages, and they burst out, and ping, and your immune system knocks them down to nothing, and they hide out in another macrophage. A few hours later, ping, another one pops open. So day after day after day, and eventually your immune system just breaks down. It can no longer cope with the viruses that are coming out, and your immune system gets so compromised that other infections can take over and destroy it. So people don't die of the HIV virus. They die of the HIV virus destroying their immune system. And so they get things like Kaposi's sarcoma, or something called wasting disease, or pneumonia, or other opportunistic infections. And when their immune system breaks down, they get highly infectious again. Now, this is very unusual for an epidemic, so maybe this is the cause that it doesn't grow exponentially. Maybe having this long delay of not being infectious, the two pumps. So we took this model, remember the multiple stages? So 2 weeks, 2 to 3 weeks, highly infectious, 6 to 8 years, not very infectious, you don't know it. You start getting infectious again, not feeling too well. Now you feel really bad, but you're highly infectious, but you stop having, spreading the virus. So we put it in, and we solve the epidemic, and we can solve even this one almost analytically. No matter what we do, this model always produces an exponential.
Is it true that on the retrovirals that have come out recently, even in later, longer stages, you can be basically non-infectious?
Well, you drive it down to infect someone, you actually have to pass on the virus. Mm-hmm. And the retrovirals drive the levels of free virus down to such small levels that the chances of infection someone is very, very small. So in the models, you can actually, you want to show this curve. You're out here, when you take the retrovirals, you can't even see the curve on here. And so you would no longer, the models can take account of that. And these models have shown the effect of retrovirals long before the announcement came out in Science. 20 years ago, we're saying if we can find some way to drive the viruses down. But so you still can infect someone, but the chances are very, very small. Because people who've been on the retrovirals, you can't even detect the virus. And when they do detect it, it looks like it lives inside the gut. A lot of that work's being done at the primate center across the lake here with chimpanzees. So this wasn't the answer. So we said, well, what else is different about this? Well, for flu, like I said, we're all in the room with each other. We can infect each other with the flu. HIV/AIDS, that's not the case. You don't randomly have sex partners or share IV drug needles. And so, in fact, some people have lots and lots of partners. So like the people visiting the bathhouses in the early HIV epidemic was called the gay epidemic. A lot of the homosexual men had giant, had hundreds of partners per year. And then a lot of the population only had 1 or 2 partners per year. So we said, let's take the population, we'll divide it up. We'll have some people have lots of partners and others have few, and we'll go get the data to find out what the real world is. And at that time, very little data was out there. In fact, the best data was still from the Kinsey reports from the 1940s. So this is the 1948 Kinsey data, and these are the number of sexual contacts per week, and these are the fraction of the number of people with that many contacts per week. So this is, I can't see it down here. So this is like 1 or 2 partners per week, or sorry, 1 or 2 partners per year, and we have thousands up here. And over here we have 3 partners per year, and then over here we have 10 partners per year, and over here we have, say, 100 partners per year. Okay? And it turns out the population is distributed as an inverse cubic. So you're doing a log-log scale. It's the slope of this curve tells how fast the probability distribution decays out. So it's what they call a fat tail distribution, or power law. There are a lot of people out here that have a lot of partners. It's not a normal distributed Gaussian or anything. And the other thing that's interesting about a cubic is that's the barrier between having infinite variance and finite variance in a statistical sense. Variance means the amount of variability that we can have in our society. So we're kind of being as variable as possible, but keeping it within bounds with having finite variance or finite standard deviation in a statistical sense. And so this was 48. In the last 5 years, this has been reproduced in study after study in mostly Scandinavian countries. We do have our partners, and the distribution of partners is an inverse cubic power law distribution. So let's put this in our model. That could be it, because you have these people out here who are going to be driving the epidemic, and there's this distribution of people. So we said, okay, let's divide it up with the people having 1 partner per year, 2 partners, 3 partners, 4 partners. We took the whole population up to hundreds of partners per year, and we went ahead and kept in the multiple stages. And we solved it, and we took we assumed that people were distributed, that, according to how many partners we had, that we call that their risk, and that they mix randomly within the population. So here's the population. It's an inverse cubic. So here's 0 partners per year, 100 partners per year. This is the number of people. And no matter where we started the epidemic, quickly the people at high risk got infected. And this is 4 years, 6 years, 8 years, 10 years. But then epidemic was always, very quickly after 2 or 3 years, was in the low risk population. We can figure out what in the heck is going on. The other thing we noticed is that no matter what we did, it was exponential growth. So 2 things were happening. We didn't get exponential growth, and the epidemic was in the low risk. Now, why would that be? It's because in the model, we assumed that people mix randomly. So this guy out here with 100 partners per year, he randomly picks 100 people from the population for his partners. We have so many people out here with 1 or 2 partners per year. When he picks his 100 random people, almost all of them are going to be in the low risk population. Okay? So that was built into our model kind of behind the scenes, and that's just not the way people are. People at high risk have high risk partners. People at low risk have low risk partners. And so we flew out to Berkeley of something called the UC Berkeley Survey Research Center and asked them, and we got some data. And sure enough, people with 75 partners per year have partners with between 60 and 80. And people with, say, 5 partners per year, their partners have between 3 and 8. We really have this narrow band of picking our partners. And it turns out not only in the risk, but also with economic status and age and educational status. We tend to have partners similar age, similar economic status, etc. So we could put that in the model. And we call it our BOF model, birds of a feather. Birds of a feather fly together. You pick your partners that are close to what you look like. People with few partners have partners with few partners, and people with lots of partners have partners with lots of partners. The epidemic is completely different. Now, when we look at it, no matter where we start the epidemic, the people out here with 100 partners, high risk, quickly become infected, but they only infect other high-risk people. Yeah?
I mean, does this information go along with the use of like condom use or anything else to help with sexually transmitted diseases?
It does.
I'll
talk about that in a little bit.
Okay.
In this case, the key, we could also use condom use. And you can look at condom use, and I bet it's an inverse cubic.
Yeah.
I have no idea, but that's my guess.
Yeah, I just didn't know if it took it into
Yeah. But what happens now is that instead of now after 5 years, it's still at 10 years, it's only moved to here. It's moving much, much slower. And it's slowly like this wave of infection going into lower risk. Okay? And now we ask how many people are infected. We have to integrate. Now if we sum all the number, these are how many people are infected after 10 years, after 15 years. We sum up all the new infections, and it turns out this is the determining curve. And it's the inverse of this curve is how we expect the number of new infections to grow. So the early epidemic is always a polynomial until it gets into this low-risk region. And that polynomial is the inverse of this curve. This curve we got from the Kinsey report to be an inverse cubic. So it says we expect the AIDS epidemic, in fact, any sexually transmitted disease with low infectivity to be growing as a plus cubic polynomial, not exponentially. So we used, through the mathematical model, we understood why AIDS was different than the other epidemics. In fact, we could even quantify where the numbers came from. In hindsight now, I can go and describe this. I can tell you it's not growing exponentially because we don't mix randomly. We tend to have partners that are very much like ourselves. And again, I don't need the model. I've got a fact. I know it. Okay? Now, here's some other things that we've learned, and I'm not going to go into these in detail, but things we've used the model for, in particular is condom use. So in syphilis and gonorrhea, if you get people to use condoms half the time, it has almost no impact on the spread of the epidemic. If you get them to have half as many partners, the epidemic spreads half as fast. With HIV/AIDS, it's the opposite. If you get people to use condoms half the time, the epidemic spreads half as fast. If you get them to have half as many partners, it doesn't seem to make a big difference. It spreads about the same speed. Now, when HIV/AIDS came out, we were fighting it just like we fought other sexually transmitted diseases. We knew how to fight syphilis. We knew how to fight gonorrhea. We were learning how to fight herpes too. So we applied the old tools with the understanding that this is a new sexually transmitted disease. But when we ran our models, it turned out what was good for one had no impact on the other, and what had no impact with one was good for the other. Why were they so different?
Is that because there's skin-to-skin contact for transmission and not fluid transmission?
No, it has to do with infectivity. So gonorrhea and syphilis are so infectious that you affect almost every partner. If someone's infected, it affects almost every partner they have. So if they have half as many partners, they infect half as many people. Okay? If they use condoms half the time, doesn't matter. They'll still infect the people. If they slip up once, the person's going to get infected. Okay? With HIV/AIDS, remember I said it's only about 1% as infectious as syphilis and gonorrhea. So you don't typically infect a partner if you have a partner. It's how many contacts you have that matter. So if you protect yourself for half as many contacts, you're spreading it half as fast. Now, well, why should it matter if you have half as many partners? Why should that matter? Well, it turns out when you do the surveys, people are willing to have less partners, but they aren't willing to have less sex. So they may go from 100 partners to 50 partners per year, but they have the same amount of sex with the 50 as they have with the 100. And it's the amount of contacts that matter. It's not the amount of partners that matter. Because of the 50, you may infect one or two. And so things like that we can see with the models. And after you explain it, it's the infectivity is the key. Now we can understand this when a new disease comes. Another example is contact tracing versus random testing. When a new epidemic happens, or like for the foot and mouth, you find that for HIV/AIDS, the early response was contact tracing. We find someone's infected. We ask, who might have you passed the infection on to and who might have infected you. And you go out and you test them. It's gumshoe. You got to go, you meet them, you got to explain it to them, you got to sign consent forms, you test them, and then you ask them, tell me all the partners you've had. People don't like to do this. It's very expensive, very time consuming. But in what random testing is, you test every piece of blood you can get your hand on. People go in for a cholesterol test, you test it for HIV. You go in for a pregnancy test. You do anything. Anytime you get your hands on blood, you test it for HIV. Very cheap test. Okay? In the early epidemic, random testing gives you almost no information because almost every piece of blood you test is going to be negative. Whereas contact tracing, you find out where the epidemic is, and you can go and find out specific individuals, okay, that are infected. So although it's costly, you find the people that are driving the epidemic. After the epidemic is infected a small fraction of the population, maybe 1 or 2%, then it switches. Now, random testing is the most cost-efficient way to find out the infected population, and contact tracing is a lot of money to find the same people you would have found the other way. And the question is when does that cost-benefit ratio cross? And HIV, and the models can give you an explicit number for that, depending upon, you can put in, this is what it costs us to trace back one person, and this is what it costs us to test 1 unit of blood. And we can put those numbers in the model and run this virtual simulation to find out really what's going on. They're being used now to design partially effective vaccines. So a vaccine is only, say, 20 or 30% infectious or effective do we use it. Models are being used actually to design the vaccines. There are about 12 clades, different strains of the HIV virus out there. And you can't put all strains in your vaccine. You can only typically put 3 or 4, or design a vaccine that can only protect against about 3 or 4. Just because you just can't put enough inoculant in it. And they're using models to design how, essentially design materials by design, to how to design these. And the first trials, major trials, were stopped abruptly about 2 years ago now. Blind trials, you get the vaccine, we vaccinate you with sterile water, and we look a few months later, and the people that got the vaccine were getting infected at a higher rate than those that got the placebo. So the trials were stopped very quickly and quietly. But the question is when does it become cost effective to vaccinate, even though it's not 100% effective? That we can look at. I was just checking, one of the biggest things we did was estimate the hidden epidemic from the AIDS data. It takes 8 years from infection to AIDS. In the early epidemic, all we saw were the AIDS cases coming in the door. We had no idea how many people were infected. We can set up a mathematical model that takes account for that long delay from infection to AIDS case. And we can back solve the model so we can tell exactly how many people were infected. And at that time, in 86, they were saying 1.5 million people infected. In 87, 1.5 million people infected. In 88, 1.5 million people infected. Meanwhile, the number of AIDS cases were going up and up and up. We put it in the model, and we got numbers that were, now we can go back in hindsight and check them, where we're actually within 10%. It looked like there were only about 750,000 people infected in 88 and 89. And so this was all done with the models to identify what the hidden epidemic is. Okay? Now, what I've been describing is all what we call continuum-based models. Yeah.
I'm sorry, before. So these models that you've gone over are based on the folks who were traditionally the high risk, right, gay men. This has changed.
Yes, right? This has changed, and so now we have heterosexual models.
Well, my question is do you have, the fastest growing rate of HIV infection is among adolescent girls,
right,
especially in sub-Saharan Africa
and the models,
and Asia. So do you have models with infection rates and also that look at protection and vaccinations and so forth that take this extremely vulnerable?
Okay, so we get to, the answer is yes and no. Okay. One problem with modeling of HIV, in the early 90s, everybody was scared to death, and it was supported. The funding support for HIV modeling just fell through the floor during the Bush years, essentially. There are very few, these old models were sophisticated for their time. They're not sophisticated by today's standards. And today's standards, so I mentioned this probability of transmission per contact. That's a product of two things: how susceptible the person is and how infectious the infected person is. And that's not symmetric for heterosexual transmission. It's easier for a man to infect a woman than it is for a woman to infect a man. And this has to be in.
A girl.
A girl, either a man, a girl, or a woman. It goes easier one direction than the others. In South Africa, it appears circumcision among men determines how susceptible the males are, and also how infectious they are. And so these type of things have to be put in the models. There are some models now that not so much for the US heterosexual epidemic, but especially for the African epidemic and also for the Indian, that have a lot of these parameters in them. Jan Medlock, one of my former students, in fact, is heading one of the efforts. And as far as I know, the question is, what new insights have we gotten from the models that we didn't have ahead of time? And I don't really know of any really breakthroughs that we've seen in these recently. But the models right now, the modeling efforts have gone on to other things. Like we quickly jumped from modeling HIV/AIDS to modeling bioterrorism, to modeling SARS, to modeling new threats. And it's very hard to get funding to do AIDS research right now, at least from the modeling perspective. I don't think it's unfortunate, but it's just the way it is. Like NIH has got a whole modeling section called MIDAS, Models for Infectious Disease and Simulation, I guess is what it's called. Of the 8 or 10 teams that they have, none are for HIV/AIDS. They've got malaria teams, they've got influenza teams, they've got dengue fever teams, no AIDS. And so something that's kind of fallen through the cracks right now. But the models do need to go in that next direction because the epidemic, we have so under-responded to that epidemic. And we still are today. Even today, we're closing our eyes. Like it can't come here. Look, it's an African epidemic. It cannot come to the U.S., and the people are not different. People are people.
Young African girl epidemic largely.
Yeah. Okay, well, so what I've been talking about is continuum models. So when I talked about risk, that was a continuous variable from 0 to 100. Okay. What agent-based models are, we actually have individuals in the computer that we model. And an individual can have things such as age, where they live, what their risk behavior is, what their economic status is. We can have all these attributes attached to an individual. Whereas in the continuum model, these would be like dimensions, new dimensions of the problem. Okay. The other thing is deterministic versus stochastic. I've been deterministic models is what I've been talking about. Every time we run the simulation, we get the same answer, with the exception of the Rinderpest, which was a stochastic. Well, in fact, that's not the case. You meet a person, if two people meet the same, the question is what's the probability that the infection is transmitted? It's a random variable. It depends upon whether that virus hops from one person to the other. It's what we mean by stochastic. It's like rolling a dice. And the modern models today all take that into account. They essentially roll the dice to see if the disease is transmitted. So if it's transmitted between two individuals with probability 0.2, they roll a dice to see if it's transmitted. And the old models would say 1/5 or 0.2 of the virus gets transmitted every time. Heterogeneity, space, age, we need to include these. Resolution, the resolution means that we do it as a classroom spread, city spread, county spread, state, country, or the entire world. What resolution do we want to work on? Okay. The continuum models are great because we form in terms of the dynamical system, and we know everything about dynamical systems. We've been studying them for 100 years as science mathematicians. We can analyze them. We know sensitivity analysis. Sensitivity means what is the change in our prediction with respect to a change in our assumption. If we assume that the virus is only 20% probability of infection per contact, if it's really 22%, how will our predictions change? We can solve those analytically. On the other hand, we have severe limitations and the amount of detail we can put in these models. Okay? Whereas the agent-based models are done in terms of individuals. This individual has this behavior, okay? Has this age, has this, we can have, say, number of partners desired per, as a function of age. We can put this in every individual. And then we get resulting behavior. And the pluses and minuses are exactly flipped. For these agent-based models, we have almost no mathematical tools. Very little sensitivity analysis. Individual data has to be derived as a function. We have to solve the model to get the distributions for what may or may not happen, okay? But they're extremely powerful because the real world is an agent-based model or is an agent-based system, okay? We're individuals. We're not a continuum in this room. We're individuals and each of us have an age, economic status. We all have different susceptibility, we've been infected with different strains of the flu before, or different resistance to the new one coming in. And models have made that switch from these differential equation continuum models to today everything is really, the current state is agent-based. And the way we started, at least this is the one I've been involved with, is something called TransSims. So TransSims is a SimCity on steroids.